Hi, this is Jerry Pinter. Welcome to Chapter 10 on Energy and Work. In part 1 of this video lecture, we will be looking at work and power. Chapter 10 is broken up into 4 different parts. In this first part, we will look at work and power. In part 2, we will introduce the concept of energy, and in particular, we'll be looking at kinetic energy, potential energy, thermal energy, and total mechanical energy. Part 3 of this lecture will deal with work and energy theorems. In particular, we will be looking at the work kinetic energy theorem and the work energy theorem for contact forces. And then in part 4, we will talk about the conservation of energy principle. So let's start our discussion here with the concept of work. In physics, work is defined as the force applied times the distance the force acts. And this is a little bit oversimplified definition, but for right now, it's good to get the general concept. So we can think of work as calculated as force times distance. And we'll qualify this a little bit more shortly when there are angles and things like that involved. But for right now, we're going to use this definition here. The unit of work is the Newton meter, because we can see that force is measured in newtons and distance is measured in meters. Now, a Newton meter is a very important combination of units. It's the unit for work and also the unit for energy. And so we will call a Newton meter a joule, and that's abbreviated with the letter J. And that is named after James Joule, the English physicist who was one of the pioneers in the work on energy and thermal energy. So let's just start with a simple example here. Suppose I push a cart using 20 newtons of force for 5 meters. Okay, so here I am, or here you are, pushing this cart. To figure out how much work you just did, you just take the force, 20 newtons, and multiply it by the distance, 5 meters. 20 times 5 is 100. So the answer is 100 Newton meters, but of course we know now that a Newton meter is a joule. So the amount of work done was 100 joules. One of the important applications of using calculations involving work is when the force is used to lift an object up. So how much work do we do when we lift an object? Well, we have to figure out, the force and the distance for lifting something, because that's how we calculate work. So the force needed to lift an object is just the object's weight. So if we think about, this box here in our hand, and let's say we're going to lift it off the floor some height h. Well, in order to lift this box, we have to push with at least as much force as the weight of the box. And of course, the weight of the box is mg, where m is the mass of the box. So and then the distance that we're going to lift, the object or move the object is the height here. So work is force times distance. The force, remember, is mg, the weight, and the distance is h, the height. So the work done to lift something is equal to mgh, the mass of the object times g, which is 9.8, times the height of the object in meters. So here's a simple example. How much work is done if you lift 10 kilograms up 2 meters? So work is equal to mgh. So we have 10 kilograms times 9.8 meters per second squared times the height is 2 meters. And multiplying all these together, we come up with 196. And again, all these units here, they equate to Newton meters, or more simply, they equate to joules. So as long as we use the mass in kilograms, g in meters and seconds, and the distance in meters, we will have the correct units. So the amount of work done was 196 joules. Now, our definition of work being force times distance was a little bit oversimplified. For example, what if the force is at an angle? So here we have a picture of the dad pulling his son in a wagon, and the force on the wagon is along the handle here, all right, which is up at an angle. Now, it's what we can do here is take this force vector and we can decompose it into its two components. There is a component that is parallel to the ground, in other words, in the direction that the wagon is moving, and the other component is perpendicular to the ground. Now, the wagon, of course, is moving horizontally. It's not moving vertically at all. So this component of force here that points up is doing no work because it is not raising the wagon off the ground at all. Remember, work is force times distance. So the distance that this force lifts the wagon is 0. It's this component of the force vector that does all the work. All right, this is the one that is moving the wagon in the horizontal direction. So this leg, this is a right triangle here, of course, and this leg of the triangle is the hypotenuse, which is the force up here, times cosine of theta. So the work done by a force at an angle is equal to the parallel component of the force. That's what this notation means here, F with a little parallel symbol here, times the distance. Or we can just think of it as force times distance times cosine of theta. So here's an example using what we just learned in the last slide. Dad pulls his son in a wagon. He pulls at a 45-degree angle with a force of 100 newtons for a distance of 50 meters. How much work does he do? So work is equal to force times distance times cosine theta. So we have 100 newtons times a distance of 50 meters and cosine of 45, which you can do that on your calculator. And this all comes out to be 3,535 joules. If a force is being used to rotate an object, this is a form of rotational work. So basically, we don't have to, let's not worry about the derivation here. It's actually pretty simple. But the key thing is, remember, for regular work, along a straight line, which is technically called translational work, work is equal to force times distance. Remember that force gets replaced with torque when we talk about rotation, and distance or displacement gets replaced with an angular displacement, delta theta. So just by making those substitutions, we have a formula here for rotational work. Rotational work is equal to torque times the angular displacement. So as an example, a woman rides an exercise bike for 30 minutes, producing 20 Newton meters of torque while pedaling at 90 RPMs. How much work does she do during this workout? So let's figure out, we need to know the torque and we need to know the angular displacement. The torque was given, that's easy. We need to figure out how many radians did she actually turn, these pedals. Well, we know she was pedaling at 90 RPMs, so 90 revolutions per minute, and she did this for 30 minutes. And then we can convert the revolutions. Remember, there are 2 pi radians per revolution. So this gives us the total number of radians. It's 1.7 times 10 to the 4th radians. And then to figure out the work, we just multiply the torque, which was 20 Newton meters, times that displacement, angular displacement, 1.7 times 10 to the 4th. And we come up with a relatively large number here, 340,000 joules. One very important and practical application of work is that of simple machines. A simple machine is a mechanism that does the work needed to move an object by exchanging force for distance. So this will become more clear shortly when we look at some formulas here and also work out and look at a couple of examples. Basically, the idea here is that the work that we put into this machine is equal to the work output of the machine. Another way of saying this is we can only get out as much work as we put into this simple machine. All right, there's physicists sometimes say there's no such thing as a free lunch. All right, we can't get work for nothing, but we can use and exploit the definition of work to kind of do a little trick here and turn this simple machine into a force multiplier. So remember, our definition of work is force times distance. So the work put into the machine, this is the work that the person using the machine is going to do. they're going to typically input a relatively small force, all right, because our muscles are only so strong, but we're going to move the machine over a large distance, all right? And so this is going to produce some amount of work. Now we can get the same work out, but what the machine does is it basically exchanges force for distance. So what we're going to get out is a very large force with, but what we pay for is that the object is going to move only a small distance. So we're going to, this term here, the force is going to be large and the distance is going to be small. So this is an example of what is called force multiplication. So there are lots of examples of simple machines that you're already aware of. For example, levers, ramps, pulleys, gears, wrench, screwdriver, a hydraulic lift, a car jack, and you might be able to think of some more. We'll look at this an example in the next slide. The great Greek mathematician Archimedes is supposedly said, "Give me a lever long enough and I can move the earth." So what did he mean by that? Well, he understood the basic mechanisms of a lever. And the idea here is that you can see in the animation down here, we have this guy here, and he's able to lift a very heavy weight over here. All right, it's got a 1 ton, that's a 2,000 pound weight. Now, how can he possibly do that by just pushing down with his arms like that? Well, he's getting leverage, which is, comes from the word lever here. But let's take a look and see how this works from a work standpoint. So the idea here is we're going to push on this side of the lever with a relatively small force, just as much as we can push with our muscles. But we're going to move this side of the lever a large distance. Notice how he's moving this lever down a fair amount of distance. On the other side of the lever, what happens here, and these are due to torques balancing and so forth, is we get a much larger force, but we get the price we pay is that the object only moves a short distance. But a lot of times that's all we want to do. For example, if we want to jack up a car, we're going to move the jack quite a bit on this end. We're going to maybe keep pumping it up and down, and the car may just move up a couple inches, but that's enough so that the tire lifts off the ground and we can change a flat tire or something like that. So again, this is the idea of force multiplication. We're basically trading off force for distance. Another example of a simple machine that you're probably familiar with is walking up a ramp is easier than going up steep stairs. Now, you're still doing the same amount of work, but you're just increasing the distance so that the force on your legs is less because the ramp is less steep. Let's now talk about power. In physics, power is the rate at which work is done. So power is calculated by the total amount of work done up here divided by how long it took to do the work. So power is work divided by time, or P is equal to W over T. So we're going to use P for power here. Now the unit of power, remember, work is measured in joules and time is measured in seconds. So power is measured in joules per second, and a joule per second has its own unit because it's so important and shows up so much that it's called a watt. And the watt was named after the famous Scottish physicist James Watt, who invented the steam engine and basically improved the steam engine and started industrial engineering and so forth. So let's look at a simple example here. What is your power output if you push a cart with 30 newtons of force across the room 5 meters in 3 seconds? All right, well, to figure out power, we need to figure out how much work you do, and that's force times distance. And then we're going to divide that by the time, how long it took to do the work. So the force was 30 newtons, the distance was 5 meters. So 30 times 5, that's 150 joules. All right, that's on top. And it took 3 seconds to do this work, we were told. So 150 divided by 3 is 50. And our units are joules per second, or we say 50 watts. And by the way, the abbreviation for watt is an uppercase W. So we can just write our answer as 50 W for watts. Let's look at another powerful example of calculating power. So this one's a little bit different. A 50-kilogram woman runs up a flight of stairs 5 meters tall in 6 seconds. What was her power output? Well, if we think about what's happening here, when you walk or run upstairs, what you're basically doing is lifting something, right? And of course, you're lifting yourself. You're lifting your entire weight up some distance, some altitude or elevation here. That's the height of the stairs, which we're told was 5 meters in this problem. So remember that we can calculate the work done when lifting is equal to, force times distance, but remember it's equal to mgh. So her mass is 50 kilograms, g is 9.8, and the height is how far she lifted her body up, and that was the 5 meters, the height of the stairs. So these three numbers multiply together to get 2,450 joules. So that's how much work she did. Now to calculate power, of course, we need to divide the work divided by the time. So we have 2,450 joules divided by 6 seconds, and that gives us a power output of 408 watts. This is the last slide of this part of the lecture. And here we're going to put together a couple different concepts that we've learned here. In particular, we're going to see that power is related to the speed that a force is moving an object. And we'll also talk real briefly about horsepower. So let's just work through an example here. A car's engine produces a constant force of 700 newtons to keep the car's speed at 60 miles per hour, which is converted to 27 meters per second. What is the car engine's power output? Okay, so let's do this a couple different ways. The first way we can do it is we know that power is equal to work divided by the time. All right, so the work done is force times distance. So we have force times, and I'm going to write the distance here as delta x. That's our displacement. And we have force times delta x divided by delta t. Now, we can do a little trick here. We can take this force, the F, and bring it out in front, and we have delta x over delta t in parentheses. But we know that delta x over delta t, that's distance over time. That's the speed of the car. That's the velocity. So we have another expression here for power from this result here. Power is equal to the force doing the work times the speed of the object that the force works on. So in this problem, using this result here, it's actually quite simple to figure out. The power of the car is 700 newtons. We were given that. That's the constant force, times the speed of the car, 27 meters per second. And we get our power is, let's see, 18,900 watts when we multiply these two numbers together. Now, for cars and also some other industrial applications and so forth, power is not always measured in watts. It's also measured in an old English unit called horsepower. And this, goes back to the old days when horses were pulling carriages and farm equipment and so forth. So 1 horsepower or 1 HP is the equivalent of 746 watts. So in order to convert our engine's power into horsepower, we just take our number here, 18,900 watts, and we multiply it by 1 horsepower per 746 watts. So we're basically taking this number, 18,900, dividing it by 746, and we get the equivalent power output here in horsepower. The engine's power is 25 horsepower. So that is the end of this first part of the lecture. It was a nice short part of the lecture, but we've got a lot more to cover in this chapter. Remember, there are 4 parts in this chapter. So I will see you shortly in part 2.